So our next speaker is Dr. Hemant Mishra. So Hemant Mishra, you can share your screen now.
All right. Let me share my screen. Is this visible to everyone?
Yeah, it's now visible. Yeah. Let me introduce Dr. Hemant Mishra first. So Dr. Hemant Mishra is a postdoctoral fellow at Central University at the Cornell University, and he is currently working with Professor Mark Wild. And his research of interest is mathematical aspect of quantum information theory and the quantum measurement. And he's going to talk on pretty good measurement and instrument for bosonic Gaussian ensemble. So we are welcome you, Hemant Mishra, and you can start now. It's yours. The stage is yours.
All right. So much introduction. Here, I believe last time I gave talk QIQT last year. I thought going for this work.
It seems that your voice is getting broken. I think.
Yes.
Is better now? Am I audible?
Yeah. Now it's fine. It's fine.
All right. So thanks for the introduction. Last time I spoke, I think last year I spoke in QIQT. It was about a teleportation project that I was working on. Now I'm going to talk about this project, pretty good measurement for bosonic Gaussian ensembles, that I've been working on with Ludovico Lamy, Prabha Mandyam, and Mark Wilde. It's funny that Mark every time gets this, whenever someone new pronounces his name, he gets this Mark Wilde. So yeah, it's Mark Wilde, and it's always funny to hear. Yeah, so this is a paper. It's a working paper that we are in the process of finalizing. The first version of this paper is already submitted to archive. There's this archive number, and very soon we are going to update that draft. And yeah, so before beginning with the actual content of the talk, I would sort of like to give you a high-level summary of what we achieve in our paper. So in this work, we do a detailed, comprehensive study of pretty good measurement for bosonic Gaussian ensembles, as well as we study the so-called pretty good instrument corresponding to this pretty good measurement. And then what we do is, it is already known that the pretty good measurement for bosonic Gaussian ensembles is a Gaussian measurement. In our work, we furnish an alternate proof of the Gaussianity of this measurement, and we derive an explicit mathematical description of this measurement. And we further, what we do is we compute the mean square error of this measurement, which can be used to compute, to kind of say how well is the measurement performing by comparing it with the Fisher information, that sort of thing. And then at the end, we also go into this detailed study of pretty good instrument. And we show that if you have a Gaussian input state, then the output state is also a Gaussian state under certain conditions on the covariance matrix of that input Gaussian state. So here's the outline of the talk. First, we will review what quantum measurement is and what quantum instrument is. Then we will briefly review the mathematical descriptions of continuous variable bosonic systems. And then we will move to the definitions of Gaussian states and Gaussian measurement. And after these short reviews, we will dive into the details of the findings, where we'll talk about pretty good measurement, and then move to the mean square error of the measurement, and then go into the pretty good instrument corresponding to this pretty good measurement. All right. So starting with the preview briefly, a quantum system always has an underlying Hilbert space. It can be a finite dimensional or infinite dimensional Hilbert space. More generally, it's a separable Hilbert space over complex numbers. Separable means that the Hilbert space has a countable orthonormal basis. And we shall denote by script LH to be the set of bounded linear operators on the Hilbert space. And mathematically, a quantum state is a positive operator whose trace is equal to 1. And in particular, if the dimension of your Hilbert space is finite, then the set of all linear maps on the Hilbert space can be seen or is isomorphic to the set of M cross M complex matrices, where M is the dimension of the underlying Hilbert space. So now, what is a quantum measurement? Mathematically, it is given by the following family of positive operators. So EX is a family of operators, linear operators on the Hilbert space, parameterized over a parameter space with some measure on it. And each of these operators are positive. And the last equality that you see is known as the resolution of the identity map. And for example, if you have, if the parameter space is finite and you have the counting measure, then the last equality says that the sum of these operators is equal to the identity operator. And this family is known as a POVM, positive operator valued measure, and also known as quantum measurement. Now, what is a constant quantum instrument? Now, quantum instrument can be thought as a generalization of quantum measurement. Physically, it can be thought of as a device, which what does is, it's like a measurement, but it does two things. It measures if you input a quantum state, the output state, it measures the post-measurement state as well as the outcome of the state in a classical register. So mathematically, there is an instrument corresponding to every POVM. So say you have a POVM E of x, which is a product of an operator K of x, and it's adjoint. Then you consider this family of maps, script mx, which acts on T as K dagger TK. This is also an operator. And this map can be seen as a positive map, which is also trace non-increasing map. And this family of maps can be thought of as the quantum instrument. And the post-measurement state, if you have an input state rho, then what you do is the output state is going to be this normalized operator. So this is known as the post-measurement state of the quantum instrument. Very well. Now let's go to the main focus of this talk, where we are going to talk about pretty good measurement. Now, what is a pretty good measurement? Now, let's start with the mathematical description of pretty good measurement. It has a canonical mathematical description for given quantum ensemble. Suppose you have a quantum ensemble where you have, it is given by this family of pairs. Px is a probability distribution over the parameter space, and your rho x is a quantum state. And suppose it means that your quantum state is prepared in state rho x with probability px, and depending on the parameter space, you have this density operator or probability mass function. So once you have that, let rho be the expected quantum state of the ensemble, which means that you take the average of all the states, you get this rho. Then here's the construction of the pretty good measurement. So we construct the POVM as follows. The POVM is as follows. So you take P of X, rho X, multiply them, and then sandwich this product from left and right by the negative half power of rho. And it can be easily seen that it's a POVM because this is going to be a positive operator. And if you take the sum of these operators or integration of these operators, this line shows that this POVM, these operators add or integrate to the identity. So there is a small thing. You see the inverse of the square root of rho. The average state may not be invertible. So if it is not invertible, what you do is you throw in another operator in your POVM, that is whatever is left after integrating, and you throw it and you get a POVM. So it's a slight thing to like mathematically be mindful of. And in case your rho is not invertible, you take its square root and the inverse is taken over the support of that state. Very nice. So this is our pretty good measurement. We will be making use of this particular structure very often. Now, as the name suggests, it's a pretty good measurement. It's known that for if you have a finite ensemble, then this measurement does pretty good, in the sense that the error probability of this measurement in discriminating a state is not more than twice the optimal error probability in distinguishing the state. By the way, if you have quantum ensemble, coming up with an optimal measurement strategy, which will tell you what is the state of the system, it's a non-trivial problem to compute the optimal measurement for an arbitrary system. So pretty good measurement is this analytical tool that does pretty good. So it's been a focus in quantum mechanics, quantum information community. And that was the reason we started looking into pretty good measurement for infinite ensembles that I'll talk about in a moment. Now, again, in general, pretty good measurement may not be an optimal measurement, but in some cases, it is shown to be optimal, but not in general. So here are some examples, some specific classes of states for which the pretty good measurement turns out to be an optimal measurement. But in general, it is not true that the pretty good measurement is the optimal measurement. Very nice. Now, I quickly recall the mathematical structure of bosonic continuous variable systems. An n-mode continuous variable bosonic system can be represented by a tensor product of n separable Hilbert space. So each of Hj will be an infinite dimensional separable complex Hilbert space. And associated with each of these Hilbert spaces will be two canonical operators called position and momentum operators. We denote it by xj hat, pj hat. And these operators have to satisfy this relation known as the canonical commutation relation. It says that you take xj hat and pj hat, you consider their commutator, which is given by the bracket around them. It has to be equal to the iota, the negative square root of -1 times the Kronecker delta. And here are some physical examples of what bosonic quantum systems are, like electromagnetic fields and harmonic oscillators and stuff. Very nice. And what we do is that we consider this vector of canonical operators. So we denote this vector r hat, and we line up these canonical operators in this particular order and consider this vector. So this will be a vector of operators. So this CCR, this canonical commutation relation, can be represented in terms of matrices as follows. So this will be the representation where this matrix you see is a matrix whose jkth element is given by the anti-commutator of the jth and kth canonical operator in the vector. And omega is this symplectic, standard symplectic matrix that is defined like this. Very nice. And if you have a quantum state, associated with every quantum state, you have a mean vector and a covariance matrix. Here is how the mean vector is defined. A mean vector is going to be a real vector of size 2n, and the jth entry of this vector is going to be the trace of the jth canonical operator and produced with the state, and you get this real vector. And the covariance matrix is a 2n cross 2n positive definite matrix whose jkth element is given by the trace of the product of the state and the anti-commutator of the shifted canonical operators, given like this. So this is how these are just definitions I'm quickly reviewing. Very well. And another thing that will be important in our talk is going to be something called while displacement operator. It's a unitary operator. As the name suggests, it's a displacement operator. If you apply this unitary operator on a state like this, rho going to rho sandwiched between the dagger and this particular operator, then the effect of this particular operator on the state is that the mean of this state is displaced by y. So r rho is the mean of the state you started with, and the state on the right hand side has this displaced mean, and the covariance matrix remains unchanged. So that's something. Yeah, and this is how Gaussian states are defined. An n-mode bosonic Gaussian state, faithful Gaussian state, is defined like this. It's an exponential operator of quadratic Hamiltonian, defined like this. By the way, in this notation, whatever you see like matrix-like operation, so you perform this operation the way you would do with numbers. It's just that you deal with operators as if they are numbers. Be mindful of the commutative relation and everything. And this z rho is a normalizing factor, and h rho is this Hamiltonian matrix of the state, which has this relationship with the covariance matrix of the state. All right. So what is a Gaussian measurement? Gaussian measurement is given by this following resolution of identity, where this rho g, so this is given by this family of displaced Gaussian states, where rho g is a fixed Gaussian state. And it is also known as general line detection. And the Gaussian measurement is given by this kind of POVM. And we will show that our pretty good measurement is this general line detection family. And measurement in bosonic continuous variable system has seen considerable success in implementing quantum information processing tasks. And particularly useful is the system prepared using Gaussian states. And so from a practical point of view, identifying and implementing good measurement strategy for such systems is of immediate practical relevance. And since this pretty good measurement turns out to be a very interesting measurement in this regard. Holevo recently showed that this pretty good measurement of a bosonic Gaussian ensemble achieves this accessible information of the ensemble, and it is also a Gaussian ensemble. Sorry, a Gaussian. It's also a Gaussian measurement. So in our work, what we do is we find this explicit Gaussian description of the pretty good measurement, and then we derive this explicit formula of the mean square error of the pretty good measurement. And we then talk about the pretty good instrument, where we show that the post-measurement state of the pretty good instrument turns out to be a faithful Gaussian state if your input state is a faithful Gaussian state with some conditions on its covariance matrix. And we also compute a mathematical explicit description of the post-measurement state, and expected output states in these cases. So here's the setup of the problem. You are given with a Gaussian ensemble, which is parameterized over the vector space R2n. Here Px is a Gaussian density function, Gaussian probability density function on R2n, given by this standard formula. And your ρx is obtained by displacing a fixed Gaussian state ρ0 in your space, and this gives you this Gaussian ensemble. Here, these matrices and these vectors are given. Right. So also we have this average state of the Gaussian ensemble, which turns out to be Gaussian as well, whose mean vector and covariance matrix have this relationship with the parameters that are given in the ensemble. Very nice. So here's the pretty good measurement in our case. So what we prove is that it's already known. The pretty good measurement is a Gaussian measurement. What we prove is that the POVM, the construction you can see in the left-hand side, turns out to be, with some calculations and everything, turns out to be equal to the right-hand side. And if you recognize what the right-hand side is, this is a Gaussian measurement that we discussed like a minute ago. So this turns out to be this, and then if you see left-hand side, you have variable x, right-hand side, you have variable y. So these variables are related to each other by this expression, where you have this expression in terms of the parameters you already know from the ensemble. And also this sigma in this Gaussian measurement is a faithful Gaussian state with 0 mean vector, and covariance matrix of this Gaussian state is given by this beautiful formula, which you can use to compute exactly what your Gaussian state's covariance matrix is. And if you know the covariance matrix of a Gaussian state and the mean of the Gaussian state, you essentially know what the Gaussian state is. That's something very beautiful about Gaussian states. They can be completely characterized by their mean vector and covariance matrix. Very nice. Here's a proof idea. If there's something you would want to learn from this talk, it would be this thing. There's this, if you ever are working on something where you have to manipulate Gaussian operators or Gaussian states, work with their powers and everything, this is going to be useful. So in our case, we have these Gaussian states ρx and ρ, and you can write these Gaussian states in this fashion. This, by definition of a Gaussian state, they can be written like this. So P of Em corresponding to the pretty good measurement, it is given by this. So if you notice this product of exponential operators, you have 3 exponential operators. Now, the idea is to combine these exponential operators and get another Gaussian operator. And for that, what we use is this golden rule that appeared in this paper by Ludovico Lamy, Siddhartha Das, and Mark Wilde. It gives you a recipe of combining combining exponential operators of quadratic canonical operators. So here's the recipe. So you consider a quadratic Hamiltonian. You consider an operator which is given by, which is quadratic in canonical operators this way, where X is an invertible complex matrix, S is a complex vector, and A is a scalar complex number, and associate to this operator this square matrix like this, such that these zeros are added to make this matrix a square matrix. Then the golden rule says that, remember in the previous slide, we wanted to combine these exponential operators and we wanted to get another exponential operator. So this golden rule says that in order to solve this equation for h hat, all you need to do is solve this matrix equation where these matrices correspond to your quadratic operator given in the left-hand side. And solving this matrix equation is relatively easier. We can use our matrix manipulations and get the result. So this was the heart of the proof. Of course, the proof has several other steps that one has to work their way through. All right. We also compute the mean square error of the pretty good measurement. So let x be a random variable with density px, and x tilde be the random variable which takes the values of the measurement outcomes. And here's the mean square error formula that we derived. At the moment, it is just a formula, but it can be a research project where one takes this formula and compares it with a lower bound given by Fisher information and tries to see how close it is to the lower bound, because that we have a tightest known lower bound for this mean square error. It would be nice to know how close it is. The closer it is to the lower bound, the better the measurement is. So that's something one can work on. Going to the pretty good instrument, we use similar ideas here. The pretty good instrument is given by this family of operators, and we show that the post measurement of this instrument is also a Gaussian state, provided their covariance matrices satisfy one of these two conditions. And we also have this Gaussian description of the post measurement state. So the post measurement state is given by this, where the right hand side is a displaced Gaussian state, and there are these relationships. So the variable z is related to variable x like this, and the mean has this relation, and the covariance matrix has this relation. Again, these are formula given in terms of the parameters we already know, and these matrices A, B, C, and V can be obtained using this formula. So I guess this is pretty much it. So these are the takeaways which I've already discussed. The pretty good measurement is a bosonic, corresponding to bosonic Gaussian ensemble is bosonic, and we have a computationally efficient expression for it. We have a formula for mean square error, and which can be used to see the performance, check the performance of this measurement. And we showed that the pretty good instrument is conditionally Gaussian, and we have an explicit description of the post-measurement state for the Gaussian input states under certain conditions. So thank you so much for listening. And if you want to look at the paper, here it is. You can scan with your mobile and it will pop up. Thank you so much.
So thanks, Hemant, for this beautiful talk. So now our session is open for few questions. So participant can ask question to Hemant.
Thank you for your talk. Could you please explain what is the meaning of ensemble? So this is a group of Gaussian states, or?
Yeah, it's a nice question. Thanks for asking. So an ensemble is just you have a family of states distributed with some probability distribution. So that collection, that quantum system, can be seen as a Gaussian, like an ensemble of quantum states. And for Gaussian ensemble, what we have is the states that you have, they're all Gaussian, and they are distributed with Gaussian probability. And it makes sense in the continuous parameter space, such as this R2N. So you have this Gaussian probability distribution function, and your system consists of these Gaussian states with this probability distribution in the system.
It's clear. Thank you.
Yeah, thanks.
Any other question from any other per audience? If it is not, then we will move toward